We are ready now to start looking at the next portion of our practice where we are moving on to working with a transformation of our f of x function. So what we're looking at on 6 through 8 really focuses on this new function that we're defining, g of x, which is equal to negative f of x. So what we want to look at here is what that negative actually does to our function. We're hoping that our students will remember from the transformations unit that opposite of, remember, these are y's. So if we negate our y, that we are actually reflecting that over the x-axis. So we're hoping that our students are able to visualize. If not, you may want to use some graph paper, some tracing paper. You can use multiple copies of the f of x graph printed out, but we want them to be able to recognize that what that reflection g of x will look like is something here, where everything we have for f of x just gets reflected over that x-axis. These are the new shapes that we have, the new forms that we're going to look at for g of x. G of x being just the blue part, just this portion that is reflected over, not the entire thing. Otherwise, it would not be a function. So in looking at our questions for this portion of the practice, they want us to determine that total area between g of x and the x-axis. Again, they can work through that, but our goal with this is to help our students to have a deeper understanding of the concept of area and functions and transformations and how we can use those ideas to answer some of our questions without actually having to calculate things. So in looking at the fact that a reflection is a congruent, it is a rigid transformation, then our function will be the same between the function and the x-axis, so it will have the same area as the original function. Classify each of the geometric figures formed between the two graphs. So notice that the x-axis is not involved here. We are going all the way from the top to the flipped over portion on the bottom. That means that we have an entire circle now, a rhombus, and an irregular hexagon. Irregular is a vocabulary word that the students should be familiar with. And then finally, what is the area enclosed by the graphs of f of x and g of x? So because we know that between g of x and the x-axis was 9 pi halves and plus 13 halves, and we know the same was for between the f of x function and the x-axis, if I'm now going between both of those, my total area will be twice that amount, or 9 pi plus 13, which is a much simpler, time-saving, straightforward way to think about this, rather than having to actually calculate the area of the circle, the area of the rhombus, and an area of a hexagon, which they probably are not familiar with up to this point. So that is our portion 6 through 8. What I'd like for you to do now is take some time to look at 9 through 11. Go ahead and pause the video, work through 9 through 11. When you're ready to come back and check your solutions, then go ahead and press play. We're ready to look at our solutions for 9 through 11. So in looking at 9 through 11, we are given a new function. We are given h of x is twice our original function. What is that total area between this new function that is twice as tall and the x-axis? They give a hint to you here because an ellipse is formed as to how you would actually calculate the area of that ellipse. What I'm hoping that some students will pick up on, though, is that, well, if my function is twice as tall, then my area will be twice as large, and I'm able to then get 9 pi plus 13. If they actually use the formula for the area of an ellipse, and they figure out what each individual area is and add them together, we should still get 9 pi plus 13. For part number 10, we're hoping that if they didn't pick up on this scalar factor here in number 9, that they will now for number 10, because if my new function is 4 times my original, my total area will be 4 times the original and be 18 pi plus 26. What 11 is asking them to do is to actually compare those to the original and to state what we know. We know that if we have a factor with our original function and that a is positive, that that area is just simply a dilation. It is a scalar of our original function. So at this point, we're ready to move on to the next portion of our practice, to looking at 12 and 13. So take a moment, try to work 12 through 13, pause the video, and when you're ready to check, come back. We're ready to check 12 and 13. If we're looking at 12 and 13, what they're asking us to do here is to still find that total area underneath the function f of x, but now we have different boundary lines than the x-axis. This is where, again, having tracing paper, or you could display the graph on your whiteboard and have students use dry erase markers and work this together as a whole class. We want to take a look at what that would actually look like. So if I'm looking at this graph, the lines that I'm now being bounded by is y is equal to -1, x is equal to -3, and x is equal to 9. So not only do I have the original area that we started with, but I also have this area down here on the bottom. Rather than trying to determine what the area of this entire shape is that is now no longer just a semicircle, we can decompose this into the original area that we do know and the area of this rectangle on the bottom, which is a 12 by 1. So in doing so, we can take our original area and add to that the area of the rectangle to get 9 pi halves plus 37 halves. The same can be said on 13, where I'm taking my original function and translating that up 1. Again, seeing what that visually looks like, you should be able to see that we have our original function plus the area of a 12 by 1 rectangle, giving me the same area that I had here, which is 9 pi halves plus 37 halves. So we're ready to look at the next portion of our graph. This is the final portion that we'll be looking at that starts to move away from the transformation portion and the area portion to other concepts such as increasing and decreasing and equations of our lines and equations of our functions. So this is really where the connection, again, from what the standard is in geometry to where we are expecting them to go with it. And for students, knowing where they're headed is very important, because we want them to understand that the skills that they're learning are not just something that they learn for geometry, but something that they will be expected to recall and use later, and that the learning does progress as they continue on with each of their advanced courses. So take a moment, look at 14 through 18, and when you're ready to check your solutions, press play. So we're ready to check our solutions for 14 through 18. What we're looking at the beginning of these is intervals of decreasing and increasing. So you can allow your students to use interval notation. This may be something that they are not familiar with. So if you would like your students to use more traditional notation from middle school, then they should be familiar with this sort of notation where x has to be between 0 and 3. But this is a great time to introduce that notation to them as well, and discuss the brackets being used when you have the equal to, which should be something that they are familiar with as well. So intervals of decreasing, x is between 0 and 3, between 4 and 5, and from 7 to 9. Intervals of increasing, -3 to 0, 3 to 4, and 5 to 6. Another important concept that they will be required to use in pre-calculus and AP calculus is the idea of absolute maximums and minimums, and more so the idea of what they are along with where they occur, which is the difference between 16 and 17. 16 is asking your students, what is the absolute maximum? The absolute maximum or minimums are always y values. So for our f of x function, that absolute maximum y value is 4. Where that occurs is what 17 is asking us. So how many times do we have an f of x or y value of 4? And where does that happen at? Well, that happens when x is -3, 3, 5, and 9. And finally, we want to look at number 18, where we are going back to g of x being twice our original f of x. What we're hoping our students will see here is that that absolute maximum is again just a scalar. It is just being dilated. So our original absolute maximum was 4. Our new absolute maximum should be twice that much and be 8. So at this point, we're ready to start looking at number 19, writing the equations for f of x using 5 different equations. Most of our students are going to want to use 6, and that's okay, but we do want to have the discussion with them about how we can turn those 6 equations into 5. So take a moment, try to work number 19, and when we come back together, press play, and we'll check our solutions.